Hi, and welcome to the 32nd day of Just Start Programming, the Rust programming language. Today, let's revisit once again the topic asynchronous programming, working with any number of features. I think there were a few sections towards the end of the topic that I need to understand and try things out. So if you're watching this video with me, join me once again live in one take, no shortcuts and no secrets. So let's just start programming. Okay, so here we are. Let me just quickly come back to the code yesterday. So it's still under this topic, working with any number of futures. Yeah, so I think I copy and pasted this code snippet here in Visual Studio Code. Sleep version finished. Okay. As I wanted to understand it better, um, so we did this part, we did this part also. So there is this race. Okay, so let's reset once again. Let's come back here. Let's backtrack. Building your own async abstractions. What's in here? Setting up a little benchmark. Okay, so our code looks something like this, if I'm not wrong, as 6 seconds F32. Yeah, so it's here. Okay, let's backtrack some more. Race uses std thread sleep slow race, using race to get the result of whichever feature finishes first. Racing futures. How about pin? Using pin directly with pin macro to avoid unnecessary heap allocations. Feature pin, async move, pin. Why did we use pin? Okay, so this brings us back to the very beginning. Okay, let's go through once again. Working with any number of features. So instead of having join or join 3, we wanted it to be more dynamic, such a way that you have this join macro where you have tx1, tx, and rx. Okay, and then to check all the features in some collection, we need to iterate over and join on all of them. Luckily, we have this join all function. Okay, so join all, you have vector macro, join all features, but this will not compile as the expected async block. Sync. So expected async block found a different async block. Okay, so async move and async. Expected async block found async block. Two async blocks even if identical of the same type. Consider pinning your async block and casting it to a trait. Okay, so this is where the pinning concept comes in. So each one produces future output. Okay, future is a trait. And that the compiler creates a unique enum for each async block. You can put two different handwritten structs in a vec. So you cannot put, mainly because of this rule. To make this work, you need to use trait objects. Okay, so I think that's the reason why we are enclosing it in box. Box new, box new, box new. Find all futures. But it says that the code still doesn't compile. Okay, we get the same basic error. New errors referring to the unpinned trait. We'll come back to unpinned errors in a moment. First, let's fix the type errors on box new calls, explicitly annotating the type of the futures variable. Okay, so futures annotating as vec box, then dyn, or dynamic was introduced. So the box will contain dynamic future output. Okay, but still this one will not compile. Fixing the rest of the type mismatch errors by using explicit type declaration. This type declaration is a little involved, so let's walk through it. Innermost unit type by writing future. Okay. Then we annotate the trait with dyn, making it as dynamic. Tar trait reference is wrapped in a box. Finally, we state explicitly that futures is a vec containing this item. And then, although there are three of them, their contents are very similar, so cannot be unpinned. There's still an issue here. And then consider using the pin macro. Box pin if you need to access the pin value outside of the current scope. Okay, that is a lot to digest, so let's pull it apart. Let's not implement the unpin using the pin macro. Box pin to resolve it. Okay, so let's see, box. Oh, so first layer, dynamic box, then you need to do a pin. Then finally vector. So instead of box new, we use box pin. If we compile and run this, we finally get the output we hope for. Receive more from message. Okay. For one thing, using pin box adds a small amount of, I think this one is important information here. Pin box adds a small amount of overhead from putting these features on the heap with box. And we're only doing that to get the types to line up. Okay, so because by using box, you are putting it on the heap, but it doesn't guarantee that in the heap it will be sequential. So by pinning, we're only doing that to get the types to line up. We don't actually need the heap allocation after all. These features are local to this particular function. As noted before, pin is itself a wrapper type. So you can get the benefit of having a single type in the vec. The original reason we reached for box without doing a heap allocation. We can use pin directly with each feature using std pin macro. So box is not needed. However, we must still be explicit about the type of the pinned reference. Otherwise, Rust will still not know to interpret these dynamic trait objects, which is what we need them to be in the vec. We therefore add pin to our list of imports from std pin. Then we can pin macro each feature when we define it and define features as vect, containing pinned mutable references to the dynamic feature type as in 17-9. Okay, so pin, we done this yesterday. Pin is here. Pin async move, pin async. Here. Pin async move. We got this far by ignoring the fact that we might have different output types. For example, the anonymous feature A implements feature unsigned 32. The anonymous feature B implements feature, okay, here it's describing this. Feature C implements Boolean. Okay, so this is the tuple. Join macro A, B, and C. Print line. We can use join macro to await them because it allows us to pass in multiple feature types and produces a tuple of those types. Okay, so the join macro uses multiple feature types, but we cannot use join all. This one, does it use join all? Yeah, it uses join all. Okay, so we cannot use join all over there because it requires all of the features passed in to have the same type. Remember that error is what started on this adventure with pin macro. This is a fundamental trade-off. We can either deal with dynamic number of features with join all, as long as they all have the same type, or we can deal with a set number of features with the join functions or the join macro, even if they have different types. This is the same scenario with face when working with any other types in Rust. Features are not special, even though we have some nice syntax for working with them. That's a good thing. So you select either join macro or join all. For join all, you cannot have the same type. However, with join macro, you can have different types. Okay, and then we We had this topic here also, raising futures. We join futures, the join family functions and macros. We require all of them to finish before we move on. Sometimes, though, we only need some future from a set to finish before we move on. Kind of similar to racing one future against another. Okay, so there's a race. Then there's this TRPL race to run two futures, slow and fast against each other. Slow and fast. Okay, did we have this? Let's see. Pin, we had pin. Okay, so race is here. A, B, A, B. It's not slow and fast, but I think we get the idea. So slow async. This one takes 100 milliseconds and fast. So so there will be a race. So fast will be returned. Each feature prints a message when it starts running. Pause for some amount of time by calling awaiting sleep. And then prints another message when it finishes. Then we pass both a slow and fast to race and wait for one of them to finish. The outcome here isn't too surprising. Fast wins. Unlike when we use race back in our first async program, we just ignore the either instance it returns here because all of the interesting behavior happens in the body of the async block. Yeah, so either was ignored because we're only concerned with this one. Notice that if you flip the order of the arguments to race, the order of started messages changes, even though the fast future always completes first. Let's try this out. Let me comment out this part. Duration. Let me insert it somewhere here. Cargo check. Slow started, and fast finished. Slow started, fast finished. Then it terminates. Okay, so the book was saying flip the order of the arguments to raise, the order of the started message. Arguments to raise changes even though the password always completes first. Okay, so it has something to do with this one. So if we change this to this one to slow, then it was saying that fast started will be displayed first, and then slow started, and finally fast finished. Okay, let's see. Run is at 33. Let me try. Okay. Fast started, slow started, fast finished. Yep. So if we switch the order, fast is going to be executed first. Okay, so that's interesting. Okay. Yielding, okay. Yielding control to the runtime. Simulate a long-running operation. Introduces a slow function. Slow 64. Then here you have an option to increase the milliseconds. Do we have that? Let me comment out this one. I think it is this part. And then you have slow here. Was it using slow? Not yet. Okay. So this one is using thread sleep instead of TRPL sleep. So that calling slow will block the current thread for some number of milliseconds. You can use slow to stand in for real-world operation. They are both long-running and blocking. So it's just to simulate. Thread sleep will block the thread. Okay. So here we use slow to emulate or simulate doing this kind of CPU bound work in a pair of features. Okay, slow 30, 10, 20. From millis 50 await. Then B 75, 10, 15, 350. 50 await. To begin, each feature only hands control back to the runtime after carrying out a bunch of slow operations. Run this code, you will see the output. Okay, because slow, this one will be called and the sleep is blocking. Yeah, so this is thread sleep. This is not sync await. Thread sleep, and then there's a thread sleep here and await. Okay, because now you have a sync await. Erase A, so A will be called first, then B started, and A finished. A finished because A is much faster. You can see the huge difference. You have 350 here. Over here you only have a small number of, or a shorter number of duration. 1 ms, 1 millisecond. So this time it's using duration from millis. Okay, so async, is it the same? Yeah, async. Started slow. Oh, so here you have slow, which is thread sleep, and then over here you have sleep and wait. So now it's a combination of thread and then TRPL sleep. That's the output. A started, A ran for 30 milliseconds because of slow. B started. Oh, okay, because this one is await. Await. Because of await, then it was able to execute this. Then B ran for 75, A ran for 10. Okay, because 1 millisecond was probably over, then A ran for 10, B ran for 10, A ran for 20, B ran for 15, finally A was finished. Did B finish also? No, B did not finish because this one took some time. Features swap back and forth each time one of them hits an await point. Each time one of them hits an await point. Okay. We could break up the work in whatever way makes the most sense to us. So it's just to illustrate, we can do it like this also. Okay. Don't really want to sleep here, though we want to make progress as fast as we can. We just need to hand back control to the runtime. You can do that directly using yield now function. Okay. So we replace all those sleep calls with yield now. So TRPL sleep is changed to yield now. Okay. So the actual intent and can be significantly faster than using sleep because each timer, such as the one used by sleep, often have limits on how granular they can be. Previously, okay, so sleep 1 millisecond. But in this case, it's much faster. Yield now. Okay. So modern computers are fast. They can do a lot in 1 millisecond. That's the reason why we have yield now here. So to prove that, this one is, instead of 1 millisecond, it's 1 nanosecond. And start here is instant now. So if we do something like this, sleep 1 nanosecond, then await. Let time instant now minus start. What is start? Okay, start is instant now. Then here you do another instant now minus start. So time is the difference. Yeah. Let's start instant now once again. Okay, so sleep was nanosecond. Yield now depends on the CPU. Then this one will show the difference. Okay, so there was a difference. The version with yield now is way faster. Oh, okay. I think we were trying out this one yesterday. Let's go to 33, then run. yield version. You can see the difference. This is smaller, so smaller is better. So yield now is definitely much more faster compared to slip. Okay, then building our own async abstractions. We can build a timeout function with async building blocks we already have. When we're done, the result will be another building block we could use to create still more async abstractions. Slow sleep duration from millis. Oh wait, I finished. Match timeout. Where's timeout? Oh, timeout is here. Okay, timeout slow duration from millis. Await. Match timeout. So this one will return something. Okay. Wait. Okay. Message succeeded with message. Error duration seconds. Needs to be an async function itself so we can await it. API for timeout. So it's a sync, accepts future, and then no, it's a type future. First parameter is a future. Max time. The result is future f output duration. Okay, so this is timeout. Now let's think about the behavior we need. We want to raise the future passed in against the duration. We can use TRPL sleep to make a timer future from the duration and use TRPL raise to run the timer with the future the caller passes in. You also know that raise is not fair, falling arguments in the order in which they are passed. Yeah. So we have seen that previously. So the first parameter is always done first. I mean process first. Thus we pass future to try to raise so it gets a chance to complete even if max time is very short duration. If future to try finishes first, raise will return left with the output from future to try. If timer finishes first, raise will return right with the timer's output. Okay. We have this one then. Okay, so let's copy this one first. Let's close this. We add it here. Okay, we don't need the slow anymore. And then here, I can comment this out to this point because we still need to enclose everything in runtime. There's a runtime. Yeah, here. This one, unclose delimiter. Did I miss anything? Oh, okay. So we need one more. And then we copy within the runtime block this, put it here. Okay, so what does it do? If the future to try succeeds and we get left output, okay, so there's a race future to try, so it's a race between future to try and sleep. But what is max time? Max time would be this, so either left, so race is okay, actually having either left output, okay, output, right error max time. Okay, if the sleep timer elapses, instead we get a right, we ignore this one with underscore and return error max time instead. With that, we have a working timeout built out of two other async helpers. If we run our code, it will print the failure mode after the timeout. Failed after 2 seconds. It failed after 2 seconds. Okay, because this one takes 5, this one takes 2, so there will be a race between timeout, future to try, slow, this is slow, and then you have a sleep. Output slow is 5, so it will execute error. Yeah, it will execute error. Okay, why error? Because future to try is slow, which is 5 seconds. And since this is a race, this part, max time, okay, so max time is only 2 seconds. Of course, although we are seeing it as timeout here, but in here it's a race. So this one will yield first. So it means that it will execute this part. Yeah, failed after 2 seconds. We can run this one. Jump to 33. So it's easier. Then we click on this. We jump to the end. Okay. Yeah. Failed after 2 seconds. Okay, so because feature compose with other features, you can build really powerful tools using smaller async building blocks. In practice, you usually work directly with async and await, secondarily with functions and macros such as join, join all, erase, and so on. You only need to reach for pin now and again to use futures with those APIs. So pin is used here. The async and await approach with join. We've now seen a number of ways to work with multiple futures at the same time. Up next, we'll look at how we can work with multiple futures in a sequence over time with streams. So yeah, that's the next topic. We use vec with join all to wait for all of the futures in some group to finish. Okay, so multiple futures. We used vec and join all. but with join all, what's that? I think there was a limitation. Okay, kept on coming back to this join all. Join all, erase, okay, join all. That's the reason why we have this pin approach. Join all as long as they have the same type. But if you have different types, then you use join macro. Okay, join all, same type. Join macro of different types. How could you use vec to process a group of features in sequence instead? Yeah, so in sequence, that is pin. You have to pin it. What are the trade-offs of doing that? What are the trade-offs? What are the trade-offs? How was it? Oh, I need to come back to this again. Here, this is a fundamental trade-off. We can either deal with dynamic number of features we join all, as long as they have the same type. Okay. Venture with pin. Yeah, but we need to come back to the point where we were using pin. Okay, so it adds a small amount of overhead from putting these features on the heap with box. We're only doing that to get the types to line up. We don't actually need the heap allocation after all. These features are local to this particular function. As noted before, pin is itself a wrapper type, so we can get the benefit of having a single type in the vec. Yeah, so join all, same type inside the vec. So pin is a wrapper, so we get that benefit of having a single type in vec. The original reason we reached for box. Yeah, for box we wanted it to be the same type also, without doing a heap allocation. So using pin, you don't need a heap allocation. Yeah, so that's the trade-off. That's a trade-off. Okay, so again, join all because we wanted to have the same type inside the vector. Process a group of features in sequence instead, so we use pin. What are the trade-offs of doing that? So pin doesn't actually need the heap allocation as compared to box. Okay, take a look at feature stream. Features an ordered type from features crate. How would using it be different from using a vec? Don't worry about the fact that it's from the stream part of crate. It just works. It works just fine with any collection of features. Okay, then we move on to streams, features in sequence. We still have time. Yeah. Let's push forward. Streams, features in sequence. So far in this chapter, we have mostly stuck to individual features. The one big exception was the async channel we use. Recall how we used the receiver for our async channel earlier in this chapter in the message passing section. The async receive method produces a sequence of items over time. This is an instance of a much more general pattern known as a string. We saw a sequence of items back in chapter 13 when we looked at the iterator trait in the iterator trait and the next method section. But there are two differences between iterators and the async channel receiver. The first difference is time. Iterators are synchronous, while the channel receiver is asynchronous. The second is API. When working directly with iterator, we call it synchronous next method. With the TRPL receiver stream in particular, we call an asynchronous receive. So they're similar methods instead. Otherwise, these APIs feel very similar, and that similarity isn't a coincidence. A stream is like an asynchronous form of iteration, whereas TRPL receiver specifically waits to receive messages, though the general purpose stream API is much broader. It provides the next item the way iterator does, but asynchronously. The similarity between iterators and streams in Rust means we can actually create a stream from any iterator. Okay, so we can actually create a stream from any iterator. As with iterator, we can work with a stream by calling its next. So in stream, there's also next method, and then awaiting the output, as in listing 17-30. Okay, you have values, iterator, then you have a map, and then this is closure and times 2. Okay, here you have a mutable stream from iterator. Okay, stream from iterator, and we use the iter. Okay, well, let some value stream next await. Okay, so but this one will not compile. We start with array of numbers, which we convert to an iterator, and we call map on to double all the values. So it's to multiply. So this is 1 times 2. It becomes 2. Okay. Then we convert the iterator into a stream using stream for iter function. Next, we loop over the items in the stream as they arrive with a while let loop. Okay, so it's a stream. I don't have receive, but stream, you have stream next. Okay. Yeah, because we're talking about stream. Unfortunately, when we try to run the code, it doesn't compile, but instead it reports that there's no next method available. So no next found for struct iter in the current scope. Use create stream extension or extended. Yeah, maybe that's how you call it. Okay, as this output explains, the reason for the compiler error is that we need the right trait in scope to be able to use the next method. Given our discussion so far, you might reasonably expect that the trait to be stream, but it's actually stream ext. Okay, short for extension. Ext is a common pattern in the Rust community for extending one trait with another. We'll explain the stream and stream extension traits in a bit more detail at the end of the chapter. But for now, all you need to know is that the stream trait defines a low-level interface that effectively combines the iterator and feature traits. Stream extension supplies a higher level set of APIs on top of stream, including the next. Okay, so next method is actually stream extension, as well as other utility methods similar to those provided by the iterator trait. Stream and stream extension are not yet part of Rust's standard library, but most ecosystem crates use the same definition. The fix to the compiler error is to add a use statement for TRPL stream extension, as in listing 17-31. Use TRPL stream extension. Main, then you have the runtime, you have this here. Okay, so this time it will run mainly because we're using this one, streams. Okay, can we still make use of this one? Hello async. Still use this. Let's just comment this out, and this part also. Then use cd, what was it? Oh, trpl stream extension. Then we copy this part here. Yeah, it will compile and run it. Value 2, the value was 4. Okay, so it's just multiplying it by 2. So it's a stream. Okay. With all those pieces put together, this code works the way we want. It's more, now that we have stream extension in scope, can use all of its utility methods, just as with iterators. For example, in listing 17-32, we use the filter method to filter out everything but multiples of 3 and 5. So values map times 2. Then here you have a mutable filter, stream filter. Okay, now you have closure value. It's like modulus. This could be modulus of 3 equals 0, or value of, okay, divisible by 3 or divisible by 5. Then it will be inside filtered. Stream, okay, filtered, and then filter dot next. Await. think we can inspect it much better if we put it in Visual Studio. Comment this out. Okay, close this. Filtered is actually the return of this one. So it's a filter. Yeah, you can see here it's filter, and then filtered next. So next is using stream extension. Oh, does it mean it's using Tokyo stream? Why do I see Tokyo here? Okay, so maybe it's using Tokyo. Yeah, so it's from Tokyo. Okay, I don't know Tokyo. I haven't used it before. But yeah, so we stick to TRPL. Filtered next. Okay, so this one becomes mutable. So the value can change. Okay, so let's run this here, run here. Okay, so divisible by 3, divisible by 5, so 6 by 3 by 5 by 3 by 3 by 5 by 3 by 3 by 3 by 5. Okay, so I think you got the idea. Yeah, of course, this isn't very interesting since we could do the same with normal iterators and without any async at all. Let's look at what we can do. What we can do that is unique to streams. Okay, interesting part. Composing streams. Many concepts are naturally represented as streams. Items becoming available in a queue. Chunks of data being pulled incrementally from the file system when the full data set is too large for the computer's memory. Or data arriving over the network over time. Because streams are features, we can use them with any other kind of feature and combine them in interesting ways. For example, we can batch up events to avoid triggering too many network calls, set timeouts on a sequence of long-running operations, or throttle user interface events to avoid doing needless work. So those are the use cases. Start by building a little stream of message as a stand-in for a stream of data we might see from WebSocket or other real-time communication protocol shown in 17-33. So stand-in. Okay, stand-in is not the real thing, just like the sleep that we did last time for that race. Okay, use TRPL receiver stream extension. Okay, we add stream extension. Let me add this too also. where was it? Ext. Okay, here. Insert this. Okay. Then in main, we have, okay, this part. Get messages is missing. So let's copy this. Get message. Message ABCD. Okay. In message sent. Okay, so this one is a channel. Let channel transmit receive. Okay, transmit send this message, and then you have, why do we have receive stream here? Okay, let's read. Maybe there's a reason for it. First, you create a function called get messages that returns a MPL stream item string. For its implementation, we create an async channel, loop over the first 10 letters of the English alphabet, and send them across the channel. We also use a new type, receiver stream. Okay, so it's this one, which converts RX receiver from the TRPL channel. Okay, TRPL channel. So it returns a tuple. You have RX into a stream with a next method. Okay. Okay. So here it's being passed here. It's converted to a receiver stream so that you can call the next method. Back in main, we use the while let loop to print all the messages from the stream. Okay, back in main, while let some message. Okay, so this one actually returns receiver stream, and by putting this here, it means you can go through using next. Okay, so if you have something, you are displaying that message. Okay, so that's the idea. So let's see. When we run this code, we get exactly the results we would expect. Okay, so let's run our code. Let's see. Let me close this. Okay, so let me just go to line 33 again. And this one. Yeah. So, yeah, we got the same message. Again, we could do this with regular receiver API or even the regular iterator, yes. Though, so let's add a feature that requires streams, adding a timeout that applies to every item in the stream, and a delay on the items we emit. Okay, so where's the... Okay, duration is used here just to simulate a delay of 200 milliseconds. Oh, wait, it's a timeout. Get message timeout. Get messages timeout. Why do we have timeout here? Get. Okay, let's come back to the code. Close this. Okay, so get messages dot timeout. So it means it calls timeout from receiver stream. So it will time out within 200 milliseconds, perhaps. Okay, then here messages.next. If you get some result, so there's a match result if it's okay, a print line message. Error reason. And oh, I think this is something. Oh, we have done this before. Probably, yeah. So it's error problem reason. Okay, so does it mean results? Did we have results previously? Messages next. Message. This one is actually returning sum is option. Okay, so this one is also returning option. Okay, so it's difficult to see from here, so let's copy that code snippet once again. Comment this out. Where are we? Main. Put it here. We have everything. Receiver stream, pin and duration. Yeah, I think we have that. But why do we need pin? Oh, pin is here. Okay. So, oops. We start by adding a timeout to the stream with the timeout method, which comes from stream extension trait. Okay. Then we update the body of the while let loop. Because the stream now returns a result. Yeah, so a result. The OK variant indicates a message arrived in time. That's why we have match result. Okay, so this one arrived in time. The error variant indicates that the timeout elapsed before any message arrived. We match on the result and either print the message when we receive it successfully or print a notice about the timeout. Finally, notice that we pin the messages after applying the timeout to them. Pin the messages. Here, okay. Because the timeout helper produces a stream that needs to be pinned to be polled. Needs to be pinned to be polled. What does that mean? Because the timeout helper produces a stream. Okay, so it seems like it's a requirement. Timeout helper produces a stream that needs to be pinned to be polled. Okay, let's try something. Let's run this first and see. Jump here so that I can press this. So it works as expected. So where's the timeout? Okay, so I think it will always work like this. Probably, yeah, okay. So once we get to this, then it will probably time out. Yeah, but what I wanted to try is this statement here. The timeout helper produces a string that needs to be pinned to be polled. Okay, so why not we remove that one and see. Let's remove this pin. Okay, I don't want to pin it. And this one, remove. Get messages. Remove this. Open. There. Error, could not compile. Okay, due to what's the error? Oh, there's already an error here. Awaiting a future is yeah. Phantom pinned cannot be unpinned. Phantom pinned. So what does it mean? Something is spinning it. Okay, so here unpin is not implemented or phantom pin. I think unpin we encountered this earlier. Consider using pin. Okay, so it's quite clear. The compiler will not allow us to do that one. So just that and then uncomment this to bring it back. So this one is always a happy scenario. Always okay. It will print as expected the messages. Okay, let's move on to the next one. Okay. However, because there are no delays between messages, this timeout does not change the behavior of the program. Let's add a variable delay to the messages we send, as shown in listing 17-35. Okay, so we have, oh, this is inside get messages. Where's the delay? Let time to sleep. We have enumerate here. Did we have that? Message. No, we don't have it. Messages send. So it's before sending. There's a for loop which will have a tuple in messages. Okay, let's just copy this part. We have a for loop here as well. Okay, so it means we comment out this block. And do this await. Did I miss anything? for, oh, there's a spawn task. Okay. Spawn task. After channel, then this one. So let me comment this out. Then spawn task. Okay, there. So what's going on here? In get message, we use the enumerate iterator method with the messages. Okay, into iterator enumerate. Then it returns get the index of the item and along with the item itself, the message. Then apply a 100 millisecond delay to even index items and 300 millisecond delay to odd index to simulate different delays you might see from the stream of messages in the real world. Because our timeout is for 200 milliseconds, this should affect half of the messages. Okay, so 100 millisecond would be the happy scenario. 300 millisecond would be the timeout. Okay. Spawn task. To sit between the messages in get messages function without blocking, we need to use a sync. However, we can't make get messages itself into a sync function because then we'd return a future stream. Instead of stream, item equals the string. Caller will have to await get messages itself to get access to the stream. But remember, everything in a given future happens linearly. Concurrency happens between futures. Awaiting get messages would require to send all the messages, including the sleep delay between each message, before returning the receiver stream. As a result, the timeout would be useless. There would be no delays in the stream itself. It would all happen before the stream was even available. Instead, we leave get messages as a regular function that returns a stream, and we spawn a task to handle the async sleep calls. Note, calling spawn task in this way works because we already set up our runtime. Had we not, it would cause a panic. The runtime is in the main. Okay. Other implementations choose different trade-offs. They might spawn a new runtime and avoid the panic, but end up with a bit of extra overhead. Or they may simply not provide a standalone way to spawn tasks without reference to a runtime. Make sure you know what trade-off your runtime has chosen and write your code accordingly. Our code has a much more interesting result. Between every other pair of messages, a problem elapses. Error. Okay, so let's run this. There. Nice. The timeout doesn't prevent the messages from arriving in the end. We still get all of the original messages because our channel is unbounded. It can hold as many messages as we can fit in memory. If the message doesn't arrive before the timeout, our stream handler will account for that. but when it polls the stream again, the message may now have arrived. We can get different behavior if needed by using other kinds of channels or other kinds of streams more generally. Let's see one of those in practice by combining a stream of time intervals with this stream of messages. Okay, so merging streams. First, let's create another stream which will emit an item every millisecond. If we let it run directly for simplicity, we can use the sleep function to send a message on a delay and combine it with the same approach we use in get messages of creating a stream from a channel. The difference is that this time we're going to send back the count of intervals and have elapsed. So the return type will be MPL stream. And we can call the function get intervals. Okay, we have get intervals, implement stream, then you still have the channel, spawn a task, async move, mat count, loop, sleep duration from millis, await, count. Okay, so we use async move because here tx send count unwrap. Okay, we start by defining a count in the task. We could define it outside the task too, but it's clearer to limit the scope of any given variable. Let me just copy this. Okay, then create an infinite loop. Infinite loop is here. Each iteration, the loop asynchronously sleeps for 1 second, 1 millisecond, increments the count, and then sends it over the channel. Because this is all wrapped in the task created by spawn task, all of it, including the infinite loop, will get cleaned up along with the runtime. This kind of infinite loop, which ends only when the whole runtime gets torn down, is really common in async Rust. Many programs need to keep running indefinitely. With async, this doesn't block anything else, as long as there is at least one await point in each iteration through the wait point. Okay. Now back to our main functions async block. You can attempt to merge the messages and interval streams are shown in 17-37. Oops. Okay, let messages, get messages, timeout. Okay, so this one will not compile yet. Intervals, get intervals. Let merge messages, merge intervals. Attempting to merge the messages and interval streams. Messages and intervals. Okay. We start by calling the intervals, then we merge the messages and interval streams with the merge method, which combines multiple streams to one stream that produces items from any of the source streams as soon as the items are available. Without imposing any particular ordering, finally we loop over that combined stream instead of over the messages. At this point, neither messages nor intervals need to be pinned or mutable because both will be combined into the single merge stream. However, this call to merge doesn't compile. Neither does the next call in the while let loop, but we'll come back to that. This is because the two streams have different types. The messages stream has a type timeout stream, where timeout is the type that implements stream for a timeout call. The interval stream has a type IMPL stream. To merge these two streams, we need to transform one of them to match the other. Okay, so we have two different types. We will work on the intervals because the messages is already in the basic format we want and has to handle timeout errors. Okay, so you have this intervals, get intervals, timeout, and then you have bin again, bin macro. First, you can use the map helper method to transform intervals into a string. Okay, so it's transformed to a string. Second, we need to match the timeout from messages. Because we don't actually want a timeout for intervals, though we can just create a timeout which is longer than the other durations we're using. Hence, we create, okay, and pin it so that it's safe to do so. That gets us almost to where we need to be. Everything types checks. If you run this, though, there will be two problems. First, it will never stop. You'll need to stop it with Control-C. Second, the messages from the English alphabet will be buried in the midst of all the interval counter. Oh, so it's still quite long. Okay, so let's end here for now, and we will continue with this topic tomorrow once again. So thank you so much for joining me today. I hope you learned something as well. Before I finally end, let me thank my supporters and see you tomorrow. Bye for now.